All right, so with this video, we are going to continue with our discussion of special relativity and specifically focus on a very particular problem. And that problem goes like this. Say you have a gun, and that gun can shoot a bullet with a speed of half the speed of light. Okay, so here's our gun. You can shoot a bullet, and that bullet can travel with the speed, let's call it W, which is 1/2 c. Okay, there's nothing wrong with this. That's perfectly feasible. No law of physics says you can't do that. And so, fine, there we go. Also, what's possible is you can have a train, and this train can be moving with a speed, let's call the speed u, and that speed, let's say it's 3/4 the speed of light. Okay, also, that's perfectly fine. There's nothing illegal about this. But here's the problem. Let's say you get on this train with your gun, and a train starts going, it's moving at 3/4 the speed of light, and you shoot your bullet. Of course, to you, there's nothing weird. You shot the bullet, it hit the front of the train. Here's the bullet. Bang, you shoot it, and it hits the front of the train, and it's going just like you'd think it should. It goes with half the speed of light, it hits the front of the train in the same amount of time you think it should. No big deal. But, and remember the speed of this guy is half of c. But now, I'm sitting out here looking at you in that train, looking at what's going on. What do I see? Here's where the problem is. In the old Galilean relativistic days, for Newton and everybody like that, they'd say, well, if you can shoot a bullet with half the speed of light, but the bullet, being on the train already, is moving at 3/4 of the speed of light. So there it is, moving at 3/4 the speed of light already naturally, and then you shoot it, and it gains an additional half the speed of light of speed. And so to me, if Galilean relativity was correct, I would say v, the velocity IC, should be, well, it's the speed of the train plus the speed of the bullet inside the train, which in this case would be 3/4 of c plus 1/2 of c, which is 5/4 of c. But this is very bad. Uh-oh. What do we have? We have an object, according to us, or according to me looking at it, would be traveling faster than the speed of light. And of course, we could continue extremizing this. We could say, well, what if there's also a car that's inside of the train, and that car itself can go 3/4 the speed of light? And so you have your gun, you get into the car, the train's moving at 3/4 the speed of light, the car inside the train is moving at an additional 3/4, and then you shoot your bullet while you're in the car, and you can see you can just keep adding and adding and adding more speed and just get as high of a speed as you want. Each thing itself can't go faster than the speed of light, but by adding on top of each other, you could somehow trick the system. Obviously, this can't be true. So this version of the velocity addition that we're used to in regular old physics can't be right. Something else has to be true, and that's what we want to investigate. How can we correct this? Because one of the big rules of special relativity is nothing travels faster than the speed of light. And in fact, if you have a mass, you can't even get to the speed of light, much less pass it. So how do we want to start? Let's start with the Lorentz transformations. X prime is equal to gamma times x minus ut, and t prime is gamma times t minus ux over c squared. Right? Where the prime stuff, again, that's u inside of the train. This is what you would be seeing. Whereas x and t are outside of the frame, the moving frame. That's what I would see when I'm looking at you who's inside the train. All right, now the way we're going to handle it now is we're going to say, okay, let's take this as two events. First event, you shoot the bullet. Second event, the bullet hits the other wall. Okay? So event 1, let's call this stuff 1. That's you shot the bullet, so where are you in the train? At what time did you shoot it? Things like that. And the same for T prime and T and X. Okay, all ones. And of course, when the bullet hits the wall, we'll call that 2. That's the second event happening. So gamma times x2 minus ut2. And T prime 2 is gamma times T2 minus ux2 over c squared. And now the question is, if I were to take the difference in the coordinates of these two events, what happens? That is to say, the coordinates obey the Lorentz transformations, and this is how you transform them, but do the difference in coordinates also transform? So we say, okay, let's say x2 prime minus x1 prime. What do we get? So I'm taking the 2 stuff minus the 1 stuff, so gamma is common, so I just factor that out. So we get x2 minus x1, and then minus u is common to both, so I'll factor that, and I'll get t2 minus t1. So that's the difference for the x's. Calculating this out, x2 prime minus x1 prime, that's just delta x prime. That's the difference in the prime coordinate, x, is gamma times, notice x2 minus x1, that's just delta x, minus u times delta t. Okay? And notice the form of this transformation is exactly the same as our original transformation, except everywhere there's an x or a t, it's delta x and delta t. So yes, in this case, the difference in coordinates does transform exactly like the coordinates themselves. And of course, if you do it with the t's, you find exactly the same thing. Delta t prime is gamma times delta t minus u over c squared delta x. So there we go. Good. I now know that the difference in coordinates for two events transforms via the Lorentz transformations the same way that the actual coordinates of each individual event transform. Why is this helpful? Because now what I can do is remember what is the definition of velocity for us. Well, velocities, let's call it W, velocity, is just delta x over delta t, right? The difference in your position over time. Of course, in real physics, we're doing this with limits and differentials, but just for the ease of notation, I'm just leaving it as deltas. This does work if you go down to differentials and limits, trust me. So because velocity is defined as delta x over delta t, notice I have deltas, x's, and t's, delta x's and t's all over the place. Let me go ahead and try to divide these two equations and see what happens. So now I'm going to rewrite them just so we can look at them. Delta x prime is gamma times delta x minus u delta t. And delta t prime is gamma times delta t minus u delta x over c squared. So now I want to divide the first by the second. So I'll get delta x prime over delta t prime equals, and now on the right I divide, the gammas will cancel out, and I have delta x minus u delta t over delta t minus u over c squared delta x. And now what I'm going to do is notice this right here is a velocity. Which velocity is this? This is the velocity in the primed frame. So that is the frame that's in motion relative to the stationary observer. I'm the stationary observer in this problem. I'm the guy just sitting there on the ground watching this train go by with you with your gun. You are the primed observer. You're in the train And to me, the train is moving, so what you see are all the prime stuff, and what I see is the unprimed stuff. So I'm going to call the velocity that you see inside the train W. Okay? Velocity of the bullet, or of the, let's say, the primed frame. Or not of, in. Velocity in S prime. Okay? So that's fine. Now what do I do on the right? On the right, what I want to do is, let me go ahead and do the kind of classic trick you always see with math, and that is divide the top and bottom by something that helps me out, and in this case, I'll divide by 1 over delta t, top and bottom. And so when I do that, what happens? Well, on the left, I have W. That's good. On the right, I have delta x over delta t minus u times delta t over delta t, but delta t over delta t is just 1, divided by delta t divided by delta t, that's just 1, minus u over c squared, and I have delta x over delta t. All right, and now I'm sure you can see exactly what to do now. Notice delta x over delta t, those are velocities. So these two things, I'll call them v, and v, that's the velocity according to the unprimed frame S. According to S. So that is, according to me, I see the bullet moving with this speed, v. And u, as I said before, u, this is the speed of the speed of S prime. So w is how fast is the bullet moving inside of my reference frame S prime, whereas u is the speed of the actual primed frame itself. So w is the speed of the bullet in the train according to you, who's on the train. U is how fast the train's moving relative to me sitting outside. And V is when I look into your train, how fast do I see your bullet moving? You see it moving with W, I see it moving with V. Okay? So when I do this, what do I get? I get W is V minus U over 1 minus U times V over C squared. And there is our huge, very important velocity addition formula, the new modified version of our old Galilean transformations. Now, here, I kind of have it in reverse of what I had over here, which is U plus W. V is U plus W. Notice here I solved it for W. Thankfully, we already know how to go the other way. If we want to go the other way, we would say V is just W plus U over 1 plus UW over C squared. Right? We already saw that before. If I say you're moving to the right with a speed U, you could say, no, you're the one who's moving with a speed U just to the left. And so all you have to do when you know one of the transformations, to get the other version, the inverse, you just change the side of the velocity. So let's test it. Let's see with our particular example, what do we get? We're told that according to you, who's on the train, you have a speed W of the bullet, which is C over 2. The train is moving with a velocity of 3C over 4. And I want to know, what do I see as the speed of this bullet? Well, the formula says V is equal to U plus W over 1 plus UW over C squared. So what do we get? We have 3/4 C plus 1/2 C divided by 1 plus 1/2 times 3/4 c squared over c squared. The c squareds cancel there. And on top, 3/4 of c plus 1/2 of c is 5/4 of c, which is what we had before, which is the problem. But on the bottom, what do we get? We get 1 plus 3/8. Does this help us? Well, let's see. 5/4 over 1 plus 3/8 is the same as 11/8. The 8 and the 4 cancel to make that a 2. And so I get 10/11c, which is bigger than the c over 2. It better be bigger. Obviously, if you're in the train that's moving and you fire something, you should get faster. However, it's not going over the speed limit of c. It's still less than c. It's just not what we would have expected in our old naive days. And so good, this works out perfectly. Very, very nice. And indeed, this is how we do it. You want to know the speed of an object relative to you when that object is being moved within a reference frame that's already moving. Well, then we use these equations here. V, in this notation, V is the speed according to the person just sitting there on the ground. U is how fast the person on the moving thing is going. How fast is the moving reference frame moving? That's the train's speed. And W is how fast the object I care about is moving according to the person on the moving reference frame, on the train. All right, very nice. Now, one more thing I want to discuss, and it goes like this. Notice something here. Let's look at our Lorentz transformation for time, and it says, let's say t prime is equal to gamma times t minus u x over c squared. Right? In fact, let's do the differences. Let's say the difference between two events. Two events happened, and I want to know what's the time difference between the two events. So maybe here's our reference frame, or here's a coordinate system. Over here, at this point, time t equal to 0, you get someone throws up a ball. They throw a ball up into the air. And then over here, maybe someone else at that exact same time turned on a TV. Right? So two completely different events that have nothing to do with each other. According to you, sitting here watching, you're just sitting on the ground, and you say, okay, I saw Jim over there throw the ball and Mary over there turn on her TV, and they just happened to do it at the same time. So you would say delta t for these two events, that is the time between them, is 0. They happen at the same time. But, from here to here, there's some distance x. There, you got a person in his front yard, and then maybe his daughter is inside watching TV. So some distance away. But notice what this equation is telling you. Let's say someone is driving their car while this is happening, moving to the right with some speed u, and they're watching the exact same two events play out. What do they see? Well, normally, our old naive ways of thinking, which are very comfortable, would say, well, obviously, if you tell me those two things happen at exactly the same time, well, then they happen at exactly the same time. What in the world would make a difference with me moving along? I don't care about that. Whatever happened, happened. And don't confuse, well, maybe you're going to see things happen at a different time because it takes light a certain amount of time to reach your eyes. I'm not talking about what I literally see visually, but rather what I would calculate literally what happened. Okay, yes, when we're getting into speeds that are really close to the speed of light, and we care about the fact that light isn't instantaneously, then an object that's further away the light will take longer to get to me than the other light, but that's not the effect I'm talking about here. Okay? I'm just going to assume we've taken into account the fact that it took a certain amount of time for light to reach me. Discounting that effect, the Lorentz transformation is telling me, even when delta t is 0, my delta t prime, that is me sitting in my little car, moving along, I would say, no, it's not 0. The time between these events isn't 0, even though that's 0, because there's still some amount there. X, there is some distance between the two events. U, I'm moving with some speed. C, that's just a number. So this number is not 0. So this is a very scary proposition. This tells me that you, watching this as an observer stationary, would say these two events happened at exactly the same time. They were simultaneous. I, as some other observer, just moving along in my car, I look at these two events and they don't happen at the same time. There's some non-zero difference in time between the two events occurring. And this is a true, real phenomenon. As I said, this isn't just some, well, it's because the light took some time to reach you, so it looks like they didn't happen at the same time. No, they literally did not happen at the same time, according to me. And there's nothing in the world that says your version of reality is more important than my version. We're both right. You say these two events happen simultaneously. It is inevitable that everybody else in the whole universe that's moving relative to you would say, no, you're wrong. They did not happen at the same time. One happened before the other. Okay? And this is what's called the principle of simultaneity. Simultaneity. This principle usually, in the old days, in fact, until special relativity came along, we would say, well, if someone says two things were simultaneous, then they were literally simultaneous to everybody. But we now know some very important fact, which is, if you have two events that occur at some distance apart from each other, if one person sees them as simultaneous, then anybody who's moving relative to that person cannot see them as simultaneous. They happen at different times. Now, if delta x were 0, that is, these two events that occurred happened at the same place. So, for instance, I clap my hands. That is, one hand reached this location and the other hand reached this location at the exact same time, and it's at the same place because they hit. Then everybody would say, if anybody says they were simultaneous, everybody would say they're simultaneous, even if they're moving. However, if the two events occur some distance apart, then everybody will disagree. Everybody will say, one person might say it's simultaneous, but anybody who's moving relative to them will say, no, it's not, and they're both right. Okay? This is a very, very important aspect of relativity, the principle of simultaneity, and a lot of times, this is the thing that kind of gets you out of trouble when you think about certain paradoxes. Like, for instance, think about this one. Here's a train car. You're standing in the middle of the train car, and maybe you have some kind of a apparatus that takes a laser beam from the very center and splits this laser beam so that half goes to the right and half goes to the left. Okay? According to you, standing here watching the event inside of the train as the train is moving, so the train has some speed u, you would say, well, this part of the train and that part of the train, the laser beams hit at exactly the same time. Because of course they did. You're sitting on the train. According to you, the train's not moving. Light moves at the speed of light, and if light started from the very center and they move out to the left and to the right, then they should reach the ends at exactly the same time. However, to me, standing out here watching everything as it moves by, I would say that's not true. I say everything moves light moves at the speed of light, the same velocity you say. However, because this train is moving to the right, when the light gets split at this point and starts moving this way and this way, the back of the train moves towards that location and the front of the train moves away. So this beam of light is going to reach the back faster than this beam can get to the front, mainly because the back is getting closer and the front is getting further away. So I, outside, watching this train go by, would say, no, actually, the back hit first, the front hit second. So again, you not moving relative to the laser beam stuff, your apparatus, you say they happen at the same time. Me, watching your thing move along, would say no, because my motion and your motion are different from each other. We're going to disagree on simultaneity. Okay? Very critical aspect of relativity, but is true. Now, does this get into problems like, well, if people can start disagreeing about when events occurred, is it possible for one person to say, your mom gave birth to you on this day, but your mom was born, 20 years before, on that day, but then to someone on a rocket ship, would they be able to see the event of your birth happen before the event of your mother's birth? Because just because someone says these two events happened with this amount of time between them, and someone else says moving relative, would say, well, no, the difference in time is something different. That would be a very, very big problem. That would violate causality, cause and effect. Obviously, the effect always has to come after the cause. What would be weird would be if, for instance, you find the difference in time between the two events to be positive, and I find it to be negative. That means one thing happened first, second thing happened second for you, but for me, the second thing happened first, and the first thing happened second. Okay? That's fine unless the two events are associated with each other. That is to say, if you could send a light beam from one event to the other in this delta t amount of time, then it can never be that the cause happened after the effect. However, if you have two different events that have nothing to do with each other, that are really, really far separated, so that, for instance, I couldn't send a signal with light to the other event and tell it, hey, this second event is about to happen, prepare for it, then yes, you can have one observer would find that this event happened first, and another observer would say it happened second. But if they're within kind of causal linking, that is to say, light can reach one or the other in that amount of time, then no, you will always have cause come before effect. You will not get into trouble. So that's nice. All right, so two little topics I wanted to go over. Very important topics. The first, much more calculation-based. You have two moving reference frame and a non-moving reference frame, and you want to know how the velocity addition formula works with relativity. This is how it works. And then the other, more conceptual, simultaneity. And it turns out, if two events happened that are spatially separated at the same time according to one reference frame, a moving reference frame will always disagree. Or the other way to say it is, if you have two observers that are moving relative to each other, they will not agree on the time difference between the two events unless the two events occurred at the same place. That is, delta x is 0. Okay? All right, so that's all I have for today. I hope this was helpful, and I will see you next time.